Welcome to the ninth video lecture in this discrete math. So this will be the fourth video lecture of this week, and we will be concluding our study on the proof techniques using, and particularly in the proof technique study of constructive proof. In the next lecture, we will continue our study of proof techniques into proof by contradiction and other techniques. So to recap what we have done so far, so we saw that to prove a statement like A implies B, there can be various techniques that are there, and we have seen that for some problems, some of the techniques can be useful. One of the most important thing is to understand is which technique to apply, and we have discussed this thing earlier also, that which technique to apply depends fully on the problem. Some problems can be split up into smaller parts, or some problem can be viewed in a different way which might help in solving the problem. But at the end of the day, whether to split a problem or how to split a problem or how to look at a problem differently, everything will depend upon your creative mind. So, in fact, we will be giving lots of thumb rules for which one to apply when and so on. But in the end, your skill that you have to develop using lots of practice will be the only useful thing. Now we started with understanding how to split a problem into two smaller parts if the deduction, or namely to prove A implies B, that part B can be split up into two separate things. Or in other words, if B can be written as C and D, then we saw that A implies B is same as proving A implies C and A implies D. Now we looked at this example and we saw that if the problem is something like if B is an odd prime, then something and something, then that can be split up into two parts, namely we can split up, since there was an and in the beginning in the deduction, so we can split up into two of the parts, part A and part 1 and part 2, or first part and second part. So this was the first technique we learned for trying to solve a problem. The second one was the fact that to understand what properties of the assumption that are required. Namely, there can be a lot of redundant assumptions. And there are redundant assumptions, we would like to throw them away just to simplify the whole problem. The idea is simply that if A implies B, then adding some more assumptions, for example A and C, will also imply B. So in such cases, one would like to just throw away the C. So in fact, if we have to prove A and C implies B, and we can prove A implies B, then we would call the C as a redundant assumption, and throwing it away would be useful for making this problem simple. Now again, which assumption to be thrown or which assumption can be thrown will fully depend upon your intelligence. There are times when you will not be able to understand which one to throw and which one not to throw. In that case, you have to continue with various attempts. So for example, in this problem that we saw, after we split the main problem into two parts, in both of these parts, part A and first part and second part, the assumption was B is an odd prime. And we saw that what properties of B is required in either of the cases. So what we saw is in the first part, what we need is that just the fact that B is an odd integer, and the second one, is that b is an real number greater than or equal to 3. So these are the two parts that are there. Now after we split this one, the next technique that we applied was the direct proof technique. So we used the direct proof to solve both the first and second part. So namely, these are the constructive proofs. So a constructive proof has two parts. The direct proof, namely A implies B, you work with A and go and prove B. Or the second part, case study, is when we split the problem into smaller problems. So the first part that was there, or in other words, if n is an odd integer, then n squared is congruent to 1 mod 4. This we did using direct proof technique. I am not going through the proof technique fully. I am not going through the full proof right now. We saw that in the second example, namely where we have to prove that if b is a real number greater than or equal to 3, then 2b square is greater than b plus 1 whole square. And we saw that we can come up with a direct proof also. But the direct proof did look a bit magical. So the question was that sometimes these direct proofs do look a bit magical and it is hard to understand how to obtain them. So in such cases, we discussed another approach, namely a backward proof. The main idea is that if we have to prove A implies B, we start with the deduction that we have to get B and we massage it. We massage it or change it, and if we prove that C is identical to B, so C is if and only if B, then proving A implies B is same as proving A implies C. And since we have simplified B to C, we would possibly be able to prove A implies C in a much simpler way. We saw the application of this particular technique when we solved this, we gave the second proof of this example, and we gave the backward proof. So we started our proof from the B, in this case that 2b square is greater than b plus 1 whole square, and we worked our way through till what was required to prove was simple enough that we could prove it directly. Okay, so in other words, for the direct proof, for proving A implies B, we can start with A and go step by step and prove B. Or we can also go do a backward proof, in which case we kind of play with B, simplify it to C, and then A implies B is same as proving A implies C. So this is a very crucial technique that is applied a lot. Now there is one more technique that was there, namely sometimes we see that proving something harder can actually be easier. Or in other words, if you have to prove A implies B, and if C implies D, then if I can prove A implies C, then I would also be able to prove A implies B. So in other words, we can prove something harder. So A implies C is clearly a harder thing to prove than A implies B, but sometimes proving that harder thing can be easier. So we solve the problem, namely if B is a real number and B is greater than or equal to 2, then 2B cube is strictly greater than 3B plus 2. If this is the problem, we basically realize that there is a way of making it harder, or in other words, we saw that we kept on making this whole thing harder and harder. We started so for example here, like the b squared is greater than 2b plus 2 is a harder statement to prove than b squared plus, not harder statement to prove, but it's a stronger statement than the earlier one, which says that the 2b squared is bigger than 3b plus 2. But somehow, by making this problem harder, we are able to simplify the whole statement, and that helps us to prove the main statement. This was one more technique that we had seen that can be applied for proving a problem. The last of the technique that we have learned, which we saw in the last video, was the proof by case studies. Namely, we talk about splitting the assumption into cases. So sometimes the assumptions can be split. So if the assumptions in particular are AND, like A is equals to C or D, so if the assumptions are OR, so A is C or D, then A implies B is same as proving C implies B and D implies B. And this is the main thing to do. The problem is that how to split the assumption into parts, or meaning how to write A equals to C or D. Now this is not easy. For some problems there is a kind of standard split, for some it's not. So in the last class, for example, we saw the example that if A and B are two positive integers, then can we prove A square minus 4B cannot be equal to 2? So in other words, A square is not congruent to 2 mod 4. And in this particular case, the main technique that we applied was that we split the problem up based on whether the integer A has remainder 0, 1, 2 or 3 when divided by 4. So it basically solved it in a case by case basis, depending on the remainders. Okay. So let's take up a new problem in this video lecture, and we will again solve this particular problem. So to start with, we start with prime numbers. We have defined prime numbers in your introductory week, but just for people, just to recap, refresh your minds, here is it. So we say a prime number, P is a prime number if no other number less than P divides P. Okay. And this is an important thing. If I have two numbers A and B, if P divides A and P doesn't divide B, then P does not divide A plus B. This is something that we did in our first week, and we will be needing particular number theoretic observation in this proof. So what is the problem? The problem is that prove that the square of a prime number is always 1 mod 6 when the prime is greater than or equal to 5. So in other words, if the P is greater than or equal to 5, then P square minus 1 is divisible by 6. Now here, to start with, let's understand what is the A. So if we have to prove A implies B, right? So the A is P the prime number greater than or equal to 5. That's the prime number. That's the assumptions that are there. And what is the thing that we have to prove? To prove p square minus 1 is divisible by 6. So how can we split up the assumptions, namely p is a prime number, into different cases? Okay, here we again use the case by case basis. We split it by looking at the remainders when divided by 6. Now, when a number is divided by 6, what are the remainders that can remain? The remainders that can remain are, of course, 0, 1, 2, 3, 4 and 5. So I have this 6 cases depending on what remainders that will be left when you divide by 6. And these are the cases for which we will be solving the problem. So let's start with the first case. Case 1. So remainder is divisible by 6. Sorry, remainder is 0. That means the prime is divisible by 6. But can a prime be divisible by 6? No, of course not. If a prime is divisible by 6, that means the prime p is equals to 6k, in which case it is of course divisible by 2 or divisible by 3, right? So it cannot be a prime. By the definition of a prime, it cannot be divisible by any smaller number. But here we can see that a number which is 6 times some k, integer k, is of course divisible by 2 or 3. So thus, a prime cannot be of the order of, cannot be 6 times k, and hence the case 1 cannot exist. Okay? So case 1 does not exist. It's not a valid case. So done. Similarly, let's go for this case 3. So case 3 again, the remainder is 2. In other words, p is of the form 6k plus 2. And as you can see again, 6k plus 2 is divisible by 2, because 2 divides 6k plus 2. It leaves 3k plus 1 as the quotient. And hence again, this case cannot be a valid case. So if p is a prime number, then p cannot have a remainder 2 when divided by 6. Now, here I have left something for you to check. Note that just like we did the other two cases, I claim that the only two remainders that can be there when you divide by 6 are 1 and 5. So 0, 2, 3, 4 are not possible remainders when you divide by 6. When you divide by 6, the only two remainders are 1 and 5. I have proved that two of the cases cannot happen. You have to go home and prove that the other two cases doesn't happen. So in other words, we are left with two cases, namely case 2, which is that the remainder when p has a remainder 1 when divided by 6, and when it has remainder 4 when divided by 5. Sorry, remainder 5 when divided by 6. So now we prove these two cases one by one. So case 1, so remainder 1 when divided by 6, hence p is of the form 6k plus 1. So p square is, just square it up, 6k plus 1 whole square, which is comes down to some 36k square plus 12k plus 1, which is 6 times 6k square plus 2k plus 1. Now you might ask, why do I split up like this, like divisible by 6? Note that what is the problem we have to do? The problem is that we have to prove that p square minus 1 is divisible by 6. We have a p square here, now we have a 1 here, and we have something 6 times this. And that is the main idea, right? So p square minus 1 is 6 times 6k squared plus 2k, and 6k squared plus 2k is the integer, so p square minus 1 is divisible by 6, and hence done. So this takes care of the case 2. Now for the case 6, the last case also has a similar thing. This time the remainder is 5, so p is of the order of 6k plus 5, which means p square is, if you do the calculation everything, it comes to 6 times 6k square plus 10k plus 4 plus 1. So here 5 square left 25, which I can write it as 24 plus 1, and thus 6 times 4 plus 1. And hence again p square minus 1 is divisible by 6. Thus, to prove the fact that if p is a prime number, p square minus 1 is divisible by 6, we divide it into case by case, various cases, depending on what is the remainder when it is divisible by 6. Some of the cases cannot happen because p is a prime, and we threw them away. We were left with 2 cases, and for those 2 cases we did a case by case analysis. This is one more example of a case study proof. In the exercises that will be handed out on Tuesday or posted on Tuesday, there will be a more number of exercises for direct and proof in the case study proof. We will be solving some more of these problems in the video lecture where we will dedicate to problem solving. Thus, so far, what do we have? So for proving A implies B, we have seen a number of various techniques. Here are some of the big ones. We split the problem if B is written as C and D. We remove redundant assumptions. Sometimes it is easier to prove a stronger statement. We had a direct proof, we had a backward proof, and if A is C or D, then we split it up into cases. Now, okay, let's move on. Let's look at the following problem. Now, what are the primes that are there? The primes are, say, 2, 3, 5, 7, 11, 13, and so on, right? Now, can you prove that the primes are infinite? That means there are infinite many number of primes. So there are many ways of asking the same question. Can we say that given any big enough number, there is a number which is a prime which is bigger than that number? Or is it that the number of primes is less than some fixed number? Say, is there only 1000 number of primes? Or what? Okay, of course, we have been asked to prove that primes are infinite. So how do you come up with a mathematical proof of taking that there are infinite number of primes are not there, or in fact there are infinite number of primes? Now, for this proving this thing, we will come up with a completely new proof technique. This proof technique is what is called as proof by contradiction. So basic idea is that if you have been asked to prove A implies B, sometimes it is easier to prove not B and A is false. Now, I would like you to go and check it for yourself. These two statements are indeed equivalent. That means A implies B is equivalent to statement not B and A is false. So sometimes we will be using this thing, and this is what is known as proof by contradiction. Now, what is the basic idea behind it? The basic idea is, say, consider this example that if I have to prove that the earth is flat. Now, one way of proving it is that, okay, you say that, okay, there is a ship coming from the horizon. When a ship comes from the horizon, I first see the top of the ship, and slowly the complete ship comes out. So you argue that the earth must be round and not flat. Right? There is one more attempt of doing it. Namely, let us assume that the earth is flat. Now, if the earth is flat, then when the ship comes from the horizon, the whole ship would appear at the same time. But that doesn't happen. First the mast is seen, or the top of the ship is seen, and then the whole ship is seen. Thus, there is a contradiction. What you see or what happens is not same as what you thought would happen. And the reason is that we have assumed something, which is, let's assume earth is flat. And this assumption is wrong. And hence, we prove that earth is not flat. So this is the main way of attacking a proof by contradiction. We will of course come back next week and do a lot more problems on proof by contradiction then. So next week we will be doing proof by contradiction, proof using contrapositiveness, which is also similar to contradiction, and counterexamples. Thank you.